Oh, Bohr uses the hydrogen spectrum, all right, through his model, but the hydrogen spectrum was the only element that it could help predict. That the model could predict. So Bohr's model starts to fall apart. All right. And then Schrodinger comes along and he says that, well, they figure out that light isn't just waves, it's also particles of energy, which are called photons. So then this is the duality of light theory. Have you heard this, where light, it behaves like a wave and a particle? All right, it can do both things. This leads into the quantum theory. And you get into the Schrodinger saying that electron is a wave. So therefore, if it's a wave, it doesn't have a precise location. In the atom. And this is where you get these probability distributions, which are the blurry images of the orbitals. And you get 4 types of shapes. All right, 4 orbital types, I guess. The S, the P, the D, and the F. And you can see the S orbital is a sphere, the P orbital is a sort of infinity-looking thing. And then the D orbitals, I mean, they have different shapes, but there's one of them there. The darker the color represents the higher the probability of finding the electron there. All right. All right. And we already talked about this. Each orbital holds 2 electrons, but in all the S, like all the S holds a max of 2. The P, because there's 3 types, px, py, pz, can hold 6 electrons. D, there's 5 of them, so you can hold 10. And then the F orbital, there's 7, so you can hold, 14 electrons on 7. 7 orbital types, which means it can hold 14 electrons. Okay. This is what I wanted to get to. So, how do you relate Bohr to the Schrodinger model? So, the quantum number, all right, represents the level. All right, so 1, 2, 3, 4. Sometimes, I think in the Bohr model, sometimes they'll call it K, L, M, and N. Does that ring bells? Anybody remember the Bohr model? In the Bohr model, you could hold 2 electrons in the first orbital, 8 electrons in the next, 18 after that, and you could go to 32 in the one after that. So that's that model. So it's two electrons, 4 or 8 electrons, and then you just keep spinning out, and you add more and more electrons. Okay. Schrodinger comes along and says, no, it's way more complicated than that. And what he basically does is each orbital gets divided into suborbitals. Okay. So at the bottom here, you have the 1s orbital. And it holds 2 electrons. These are electrons. Max occupancy is the number of electrons it can hold. Then you go to 2s. And I'll show you this on the periodic table, and you'll see how it relates. 2 electrons, because each orbital. Then you get the p orbital. All right, 2p, of which there's 3 types. So there's 6 electrons total. Then you get 3s, 3p. S orbitals hold 2 electrons. P orbitals hold 6 electrons. What comes after that? 4s. 2 electrons. Now this is where it changes up. What do you think is going to come after the 4s? Sorry? Well, it's always been SP, SP. So you want to say 4p, but what actually comes before that is the 3d. So I'll do that in a different color. Do it in pink. So you get a 3d orbital sitting in there, and the d orbital holds 10 electrons. Then it's the 4p. This will make sense when you look at the periodic table. Then the 4p comes, which can hold 6. Then it's the 4d, which is 10 electrons. And then the 4f is the highest that we're going to worry about, which holds 14 electrons. So you can see when you fill the orbitals, you go from lowest energy to highest energy. So they fill in a specific order. There are exceptions. There's always exceptions. All right. S and P S is always filled first. And then it's P after that until you get to this 3D here. And if you look at the periodic table, if we flip the page, does everybody have that? Can I flip the page? Okay, so if you look at this, here's the periodic table. All right. You work left to right. Okay, so 1s, 1s, then it's 2 s's, and then it's the 2p orbitals, 3s, 3p. Okay, after that, 4s, and the next one, it's a d orbital. So this is why you don't go past the first 2 rows in grade 10. Okay, because they don't fill. Grade 10, it's a specific order. The Bohr model works, it's fine. But when you go past that, it gets more complex. All right, so then the 3Ds get filled, then the 4Ps, and then you go down here, 5S, 4D, whoop, and it keeps going like this. These ones actually get inserted into here. We'll talk about that tomorrow. Okay, so again, these lanthanides and actinides get inserted up here. And it all has to do with their mathematical, or their energy levels and their stability. So this is how we create electron configurations of atoms. So and we're going to learn how to do that. Right? We'll start that now and we'll finish it tomorrow. So if we look at fluorine, here's fluorine. Okay? Fluorine is, I should have a periodic table right beside me. pull out your periodic table. Here's fluorine, right here. The end of the second row, okay? So to figure out its electron configuration, you start with 1s, okay? And you simply write 1s. How many electrons can the s orbital hold? It can hold 2. Literally, it's like you put one electron in, and then you put another electron in, and you end up there. Okay, so 1s2. So we write 1s, and we put a 2 up there. That says the 1s orbital has 2 electrons. Then you drop down to the next one. Do I fill the s here? So I'm working. This is fluorine right here. Okay, this is where I want to get to. This is fluorine. All right. So you keep working your way across until you get there. So 2s, and they both get filled. So I write 2s with a little exponent 2. And these go across. Now I hit the 2p's. How many electrons to get to fluorine? 1, 2, 3, 4, 5. So then it's 2p, 5. That's the electron configuration of fluorine. Okay, so you can describe atoms in terms of their protons, right? How many protons they have will tell you where they are, but you also can describe them in terms of their electron configuration. All right? All right, silicon. Where is silicon? Let's find it on the periodic table. Silicon, silicon, silicon. Here it is right here. Number 14, okay? So we have to get to this part. There's silicon right there. All right. 1s2s get filled right away. The whole second row gets filled as well. 2s2, 2p6. The 3s2s get filled. How many 3p electrons are put in? 2, right? Because then it's 3p1, 3p2. That is the electron configuration of silicon. Do you want to try aluminum? It's right beside silicon. So what do you think it is? There's aluminum right there. So it's one less. Here's aluminum. What's the electron configuration of aluminum? It should be the exact same except what? 3p1. It should have one less electron, right? It should be 1s2, 2s2, 2p6, 3s2, 3p1. All right. Beryllium. I'll show you where it is on the periodic table. It's right here. There's Te right there. Think you can do it? Is it Tc or Te? Tc. Oh, it's Tc. Sorry. There you go. Tc. All right. Write out the electron configuration of Tc. Technetium. that it? Where's the weird part? I don't know if it's weird, but the change up is right there. 3 Ds get filled before 4 Ps, and then at the end, you're filling the Ds again. Okay? You literally just follow periodic table to get the electron configuration. All right. What's annoying about this method? You got to write out a lot of things, right? Like if you're doing stuff way down here, these are going to get massive. So we don't want to do that. So chemists came up with a shorthand. Okay. And it's called core notation. So what you do for core notation is like all of this stuff. If you look at 4P6, whoops. All of this, that bit there, gets me to here, right? These are the noble gases, right? These are all filled. So in core notation, what you do is you just go to the nearest noble gas. That eliminates all this stuff, and then you just write the next little bit. So at most, you have to write across to here. All right? So you always go back. So if you're going to write TC, the nearest noble gas, where's TC? Right there. So the nearest noble gas is krypton. So you just go, you would write krypton in brackets like that, and then just write 5s2 4d5, which makes it a lot easier. Okay. So rubidium, if you go to the bottom here, excuse me, RB. RB on your periodic table is right here. The nearest, right over here. The nearest noble gas is krypton. So for that one, you just write KR in brackets. And then what do I write? 5s1. That saves you having to do a whole bunch of stuff. What would you write for krypton? We'd write the one before that. So the one before krypton is argon. And then you'd write 3s2, 3d10, 4p6. All right. Does that make sense? If you just follow that pattern, you can figure out the electron configuration of everything. So I'm going to get you. We're not going to do ions yet. So if you go back to your other one, the first one I gave you, I know we're all over the place today. This one. Write the electron configuration, do full, and then you can do core. Okay? On a test, I'll only ask for core, but I want you to practice full for now. Yes, please. That's what you're doing for the rest of the block.